guys ready? Hello, everyone.
Hello.
Thank you for joining us this afternoon. So welcome to this session dedicated to CAD data preparation for real-time visualization using both Pixies and Unity. So I'm Axel. I'm a product manager at Pixies. And today with me, we have Cédric.
Hello, I'm head of research. I'll be giving you more technical details about our main algorithms.
Just to start, first a little bit about our company, Pixies. So Pixies is a software editor providing best-in-class algorithms for CAD and DCC data treatment. So our goal at Pixies is to bridge the gap between complex 3D models that are made for design or engineering and the real-time world, and in particular Unity, of course. As an introduction, let's start with a video that showed the VRED Unity plugin from Pixies. And this plugin creates an automated bridge between VRED. VRED is a design visualization software by Autodesk and Unity. So basically with this plugin, what you do, you can bring Unity, in Unity from a VRED file, a variety of information, like re-optimized meshes, materials, variants, and animations. So let's watch this short video. Oh, sorry, it didn't launch. It's demo effect, of course. Sorry about that. It's not launching. Okay, so never mind. So it was basic introduction to show what an integration of our solutions can do. Of our algorithms with the VRED example, but the idea for today's session is to take the same car model that you didn't see there, but the same example, but this time coming not from VRED, but from Autodesk Alias, so meaning straight out the original CAD solution where this model was designed. And we will follow each step of the optimization using Pixies main algorithms, and to generate out of this very large CAD assembly a real-time ready asset for Unity. So first, a little bit about CAD, because it's important. So nowadays, CAD models are everywhere, because basically almost any CAD product, manufacturers today is primarily designed in a CAD solution like CATIA or NX or Alias in this case. But it's not that easy to turn CAD models into real-time visualization material, in particular large CAD assemblies. So as I said, CAD data is meant for design, engineering, and manufacturing mainly, and it usually comes with a large quantity of information. So if we consider that the car is composed of hundreds of thousands of parts, you can imagine how huge a CAD model, a CAD assembly can be. So the main difference between CAD and real-time 3D data, are the geometry, the assembly tree, and the materials mainly. First, CAD geometry is basically a mathematical representation of surfaces and volumes called VRED. And when real-time 3D geometry is usually a mesh representation, so that's quite different. Then a CAD assembly tree is not organized for real-time animation performance. And finally, it's a common thing that a CAD model doesn't contain visualization information like proper materials, shading information, and UVs. So now, how do you go from a CAD file like an Autodesk file to meshes actually usable in Unity? Well, that's when you use Pixies solution. So with our process that we're going to show, we're going to start with the first step, which is a file import.
So in the data preparation process, the first and more important step is the CAD import. It is essential to retrieve the most accurate definition of the model to limit the complexity of the data processing. We handle a large amount of CAD file formats. Some of them are standard, but mainly they come from proprietary formats designed by CAD software editors. A CAD file contains the complete product structure of the model, and for complex assemblies, it can be really heavy. For example, our customers often come with models composed by hundreds of thousands of parts assembled in more than 10 levels of hierarchy. Moreover, advanced concepts such as assembly instantiation or property overriding are needed to handle properly these structures. In the field of engineering design, the geometries are generally defined by a VRED structure. This boundary representation is an exact definition of the skin of the object in terms of topology and geometry. We developed our CAD modeler to handle all that information and allow us to evaluate positions and derivatives on the structure. And each geometric primitive is an analytical definition of a curve or a surface, and at least 20 curves and 22 surfaces types are necessary to handle the bundle of CAD file format. So, an example of surfaces we handle are NURBS, cylinder, sphere, torus, etc.
So now we're going to dive into our model, our alias model, and the data preparation process will follow these 4 steps. So first, geometric optimization, then scene tree optimization, followed by meshes beautification, and final step will be the creation of levels of detail. But first, good CAD data preparation starts with good analysis of your model. You need to know what's inside. So first, let's take a look at how the scene tree is defined, and let's look for important information. First, hierarchy levels. Here we have 1 part per alias layer, all at the same level, which is not very practical for real-time animation. Then regarding the number of parts, here we have 158 unique parts, which is really not that big, but still needs to be merged smartly for real-time use, of course. Regarding naming, here the alias designer that created the file named the parts with specific names. So that's information that can be used as metadata during the data preparation. So, for example, interior parts, they contain ints in their names, exterior parts, they contain ext, etc., etc. So that's information we can use. Then we'll look for instances. In this case, there is no instances, but sometimes in alias files, instances are used to create symmetries. Then we'll look for empty nodes that can be unnecessary, and we will remove them if they're not necessary. And then we'll look for variants. In this case, we have the spoiler, the rear spoiler of the car is present twice, once in up position, once in down position. So we'll need to remove the down position, for example. And finally, we'll deal with the pivot points. Here, all objects have the same scene-centered pivot points, so we'll need to rearrange them so that the car can be animated later in Unity. Now, regarding the CAD geometry data, in our model, we need to look if parts are geometrically linked or disconnected, and see if it makes sense for a good visualization. So, in our case, we have only surface CAD data, and many parts are attached together. So we'll need to detach them in order to create logical groups like the left door, the right door, the front wheel, the steering wheel, etc. Then regarding the materials, alias materials have been applied to the parts by the alias designer, so directly on the CAD surfaces, and they're not suitable for Unity as is, so we'll see how we will replace them by Unity materials. Finally, it's important to look for metadata and see if they can be used during the preparation or in the final 3D experience. In that case, we'll only use the part naming as metadata because the model contains only that. So now that we have a better idea of the model we're dealing with, we can start with the first step, which is geometric optimization. So right after the import phase that Cédric told you about, the first step consists of repairing some VRED information that can prevent the creation of a good mesh later on. So basically, the repair CAD function will stitch together unconnected patches, which is important to obtain a watertight mesh during tessellation. So now, Cédric is going to tell you just a little bit more about the repair CAD, more in technical detail.
The repair CAD algorithm is a bundle of unitary processes to optimize the VRED. In some models, for example, in surfacic models, like in alias, the patches are disconnected, and we need to reconstruct a good topology over the model to avoid cracks on the mesh. Here we see a cracked mesh and the default that can appear. It is so highly recommended to sew the boundaries before the tessellation process to obtain better results in terms of quality. Here we see why this step is important, because it prepares the surfaces for good tessellation and prevents future gaps between faces. These types of default could be made even worse after a decimation process. Another kind of issue encountered is duplicated faces. The main consequences of duplicated faces after the tessellation are non-manifold edges that will bother some mesh algorithm that need a manifold topology. For example, the defeaturing function for to remove holes. Another consequence is the presence of useless duplicated polygons that reduce the frame rate. And last but not least, the well-known Z-fighting will sometimes appear with this configuration. So our repair CAD algorithm detects and removes those duplicated faces to avoid this problem after the tessellation. And the final step is the loop optimization. In some case, CAD software will split the patches boundaries in a lot of small curves. Since each curve is tessellated independently, the tessellator will generate one vertex at each extremity. So merging these curves allows a better spreading of edges on patch boundaries. Now the model is ready for the tessellation process.
So tessellation is one of the most important steps in data preparation, and it's one of our strengths at Pixies. From this mathematical VRED information we retrieve at import, Pixies has the ability to generate a watertight mesh that will be well balanced between polygon density and shape accuracy. So this LES model here has a specific part naming convention, as I said before, and we can use that to automatically determine tessellation precision parameter per part typology. For instance, we can define that the core body should have a higher precision than the chassis, or interior parts should have an even higher precision, because in Unity later, maybe the camera is meant to be very close to these parts, so we need accuracy. And so finally, the full tessellated car here is made of a little bit less than 2 million triangles, which is quite a performance regarding the complexity of the model. So Cédric will now give you more detail about this Pixies powerful algorithm.
So the goal of the tessellation algorithm is to produce a mesh with the best visual aspect near the exact surface according to some criteria. The most used criteria are maximum deviation, also called max sag, maximum angle, and maximum length of edges. The sag is used to control the maximum distance between the discretized mesh and the exact surface. In other terms, it's the precision of the mesh. For example, on a sphere, and with the same sag parameter, a big sphere will be meshed with more polygons than a small one. Another parameter is the max angle. It allows to add more elements on small curved surfaces when the sag parameter is not sufficient. This parameter forces a maximum angle between neckbore polygons. So the neckbore polygons relying on the same surface. So unlike the sag parameter, the max angle is not relative to the scale of the object, but only to its curvature. And finally, the max length parameter can be used to limit the size of the edges, usually for simulation needs. And it is generally a bad idea to use it for meshes intended for visualizations, since it will add unneeded polygons without impact on visual quality. Of course, all that three criteria can be combined during the tessellation process to adjust the quality. The efficiency of the tessellation is strongly correlated with the efficiency of our CAD modeler, because it's the CAD modeler that is in charge of evaluating point samples discretizing and computing derivatives on the VRED surfaces. So the tessellator integrates the criteria over the modeler information to generate a sufficiently distributed grid of points in the parametric space of the surfaces. And one of the key features of our tessellator is the good alignment of elements. It aligns the best it can the vertices inside the surfaces with the vertices on the boundary curves to avoid shading issue. In this example, we see the difference with and without alignment, especially on the fillet, because it's a curved area. There are other steps to handle special cases, but they are out of scope. However, it is good to know that the whole tessellation process is designed to be as fast as possible without compromising the quality of the result.
So after this tessellation process, some meshes may still be incoherent or show some problems. It can be due to the way the model was originally designed, but also the tolerance we used at tessellation phase. So in this example, we see that some non-manifold surfaces have created redundant polygons, that what appears in pink here. So we have a repair mesh function that will identify and fix those issues.
The repair mesh feature is a smart combination of functions that will repair an asset automatically. First, it repairs the connectivity of the mesh for further optimization. Here, the edges in blue are disconnected, and we can see through different configuration. If you look at the line to the right, the vertices are aligned. So we basically need to merge coincident vertices together to reconnect the mesh. But on the remaining line of edges, the vertices are not aligned at all. So the repair mesh function uses another algorithm to reconnect the edges by sewing the near boundaries. This operation creates some extra triangles, but offer a well-connected mesh suitable for optimization. The last thing to ensure a good topology is to make the orientation consistent over the mesh. The orientation is done by propagating polygon orientation to the neighborhood. In the majority of cases, it is enough, but sometimes the mesh is locally homeomorphic to a Mobius strip, making the whole mesh not orientable. In that case, our algorithm tries to cut some chosen edges to split the Mobius strip and make the model orientable. However, in complex cases, orientation problem can persist.
And face orientation is really a big issue in data preparation. So it happens very often that some faces are not oriented correctly, even after repair mesh, as Cédric said. So see the pink faces here. These are misoriented facing, meaning transparent from this point of view. So if back face culling is on in Unity, we will see through the car body, which is not what we want, of course. And reorienting faces correctly is also a performance matter, since it will let the real-time engine, so Unity, do back face culling, so it's important. And as Cédric said, the repair mesh function sets orientation per propagation, but some incoherencies remain here. It's due to the fact that we have only surfacing patches, which are very, very hard to orient. So for these cases and for these surfaces we see here, what defines which face orientation is correct will mainly depend on the user's point of view. So here we'll use another algorithm we call Smart Orient. And this function will properly orient all polygons in the same direction automatically, according to external point of views.
The Smart Orient algorithm uses visual information to detect the orientation of the model. It generates points of view near the model and uses them to detect which side of each polygon is the most visible. The strength of this algorithm is that it automatically places viewpoints on the exterior, but also in the interior. We can filter which cavities will receive viewpoints by volume. This visibility information can also be used to remove unseen polygons, to lower the poly count even more, or it can also be used for UV generation and a lot of other algorithms.
So now we finished the first step, which is geometric optimization. Now we can move on to scene tree optimization, which is also important. Because simplifying the scene tree can be important for three things. First, for grouping parts together in order to create animation later in Unity. So for that, we need to merge parts smartly. So we want to keep movable objects separated from non-movable objects. So for movable object, we'll have the steering wheel, the doors, the wheels. And on the other side, we'll have steel parts like the car body, the lights, the chassis, and other parts. And also, we need to keep interiors separated from the exterior for a cube maps generation later in Unity. Then simplifying the scene tree is also important for purification logics and also for better runtime performance in Unity. We need to limit the number of draw calls to a minimum by making the scene graph simpler. And for that matter, we use Pixies function like merge parts or compress tree or remove empty nodes and other functions to rearrange the way nodes are sorted in that scene tree. You can do that in the GUI, or you can do that by scripting using our Python API. In the end, for this car in particular, that's what we obtained. So we had 158 parts that were sorted under the root, raked. And now we have something organized logically, and we kept only 33 unique parts and the hierarchy as simple as possible. Then regarding the pivot points for later animations, well, in CAD data, pivot points are not always defined in a way that can be suitable for real-time animations. So we use functions to recursively set the pivot points of each node of the hierarchy to its bounding box center, or following a 3D frame reference. Now, third step is mesh purification. It's the process required for the meshes to look beautiful and realistic in Unity. So I mean with nice shaders and textures later. Well, in our case here, there are almost no materials nor UV information in our CAD file. So first, during this step, we generate basic UVs by simple box projection on channel 0. On the full car. Then, thanks to part naming convention we use scripting, to automatically apply different UV values according to the part typology again. And of course, some parts require some specific UVs, like the tires, like the brakes, like the screens, or like the steering wheel. And for that, we can use custom UV matrices. And then we copy UVs created on channel 0 onto channel 1. We repack all that for later baking purpose in Unity. Then regarding material assignments, we simply attach specific material name to each part according to the part's naming convention again. And the material names correspond to the very same names defined in the Unity material library. That way, the Unity materials will automatically replace the one from Alias once the car is imported inside Unity. So Cédric will now show you a little bit more about our UV algorithms, which are quite powerful also.
There are several ways in Pixies to generate UVs. First, the UVs can be generated during the tessellation process by using the two-dimensional parametrization of the surfaces. We can also uniformize this parametrization to make it consistent in 3 dimensions. Another fast way to generate UVs suitable for baking is by projection. This method induces more seams and deformation, but is fast to execute and works quite easily. And the Graal in UV generation is the automatic unwrap of 3D models to generate UVs suitable for advanced texturing. This task is usually done by 3D artists, but it is not the funniest task they have to do, and it takes a lot of time. Our algorithms try tries to find the best set of lines to cut UV island and reduce the deformation of the UVs. The strength of our approach is that we use the CAD topology information and the visibilities information to help find the best seams. When the UVs are used for baking, they cannot overlap each other. It is then necessary to repack them to ensure that each texel is used once, or repack function optimizes the UV space to save the memory used for textures.
So now that we are done with mesh beautification, we want to create LODs, to go to Unity, of course. So we want to create 3 levels there for our car model. So at this step, high-resolution LOD0 is ready. It's the model we've prepared so far, and it's made of around 2 million triangles. But to finalize this LOD, we just trigger a quick repair mesh that we showed before. And we do that because parts were merged together in previous steps, so we need to fix some potentially disconnected edges in the final meshes. For LOD number 1, we will use the mesh decimation function. And decimation in Pixies can be driven by either a polygon target or by quality control criteria. And these criteria, they can preserve the original shape, UVs, and normals, which can be very important for CAD models. We don't want things to look like a potato in the end. So for this LOD, we use the decimation with quality control. And we approximately cut the number of polygons by half here, without losing shape precision from a very reasonable distance. And so decimation is also a very, very important algorithm, and Cédric will tell you more about it.
In Pixies, there is 2 ways to decimate a model, as Axel said. The first method is a decimation driven by quality. It works by removing some chosen vertices according to user criteria. The most common criterion is the maximum deviation, which is the maximum distance between the original mesh and the decimated one. One other powerful parameter that we expose is the normal distortion control. In short, it checks the normal at any point of the mesh, even where it is interpolated, and controls the distortion in terms of angle of deviation. This algorithm can even control the UV distortion by the same way. The other decimation method that will be available on the next release of Pixies is the polygon target decimation. It allows the user to specify a target polygon count to ensure that the model fits to the performance of a given device. This method is based on edge collapse using quadric error metrics.
So to create LOD number 2, now that we have number 1, we use this decimation function with polygon target. And here we decided to keep under 10% of the original count, and it still looks good enough from a certain distance. And also, maybe in Unity we'll want to physicalize the car and use real-time shadows. So here, in this step, we also create a lightweight envelope mesh, and that will save performance to those purposes. At Pixies, we have what we call Proxy Mesh function. That's what we use here, and it automatically converts an industrial complex assembly like this one in a single wetted envelope. So you switch from thousands of parts and millions of triangles to a single low polygon model. That's what you see there. And we have other remeshing algorithms, so Cédric will show you the other ones we have.
To create a proxy mesh, we need to retopologize the object to keep only a very simple definition of the external skin. We can use the wet skin proxy mesh method, or basically voxelization with or without marching cube. We can even bake all the shading information in the proxy mesh. On this simple example, UVs are created and all the maps are baked to create a PBR material. Albedo, normal, roughness, metalness, ambient occlusion, and opacity maps can be baked. This method allows to drastically reduce the number of draw calls needed to render the scene.
So now we've completed our process to transform our large CAD model into an asset that is fit to be used in Unity for a real-time purpose. So the final step would be to save our asset as a Pixies file, and we use the Pixies plugin for Unity to import the result into Unity. So there we use the full power of our plugin to have a fast import, to automatically replace materials with the scene ones, Unity ones, and also because we have a rule engine to apply other automatic processes. So very powerful also to use the Pixies plugin. Here is the final result. It's not showing, but
this one
it's basically, sorry about that. It's a real-time experience that was built by our friend Unity and Alex Hughes in particular. So basically, it just created a full car that can be driven. That can it's physicalized. You can drive. You can change the point of view. You can change everything, the material, the tires, everything live in real time. And this shows how we can join Pixies and Unity power to create a stunning real-time experience. This one is very still, but I assure you this is very impressive. So the data preparation process is no longer an issue. There you just saw that how we can easily turn a large CAD assembly into a real-time experience. This video is on YouTube, so you can basically, sorry about that, but see that later. It's quite efficient. To finish, I just want to tell you a few words about workflow automation using Pixies. So once we have created our data preparation scenario, like we just did until now, then we can use Pixies API and Pixies batch engine to streamline the process. So basically, we have customers that connect their product lifecycle database to our cloud-based data prep engine, in order to feed their Unity experience with suitable models. But we can also do other tasks, like deliver models for experiences based on USD or GLTF, for instance, and many more, of course. And regarding the Pixies, what we are doing next, basically now we are investing in machine learning. And this will make our algorithms more intelligent and more autonomous. So for that matter, we opened the machine learning department in Montreal, and we are hiring there. So if you guys are interested, you should just contact us. The machine learning will allow different progress in CAD data preparation, which is a very tedious and complex thing to do. For example, by recognizing shapes that need specific optimization criteria, or by analyzing the model specificities to give some hints to the user to what it should do. And also to generate UV cutting lines more accurately, and we can think of many other possibilities. So thank you guys. Now it's time for questions. If you have ones, please go to the microphones that are in the middle of the scene. Thank you.
Thank you.
Yes, hi, I have a question. The process that you showed, is it fully automatically, or you just need to take control on every step that you presented?
No, it can be fully automatic. It is automatic. It's just like we decided to cut the process to show you that to show you all the algorithm we use. But basically, you can do that, interactively in our product Pixie Studio. It's meant for, there's a GUI and a powerful viewer. It's meant to do that, interactively. But also we have, as I said, a Python API, and the idea for you is to create your recipe or to automatically create the same thing. So, so you looking for your recipe, and once you're happy, you code that in Python, and you can feed that to our batch tool to do that automatically. So that's the idea.
Yes, thanks. And do you have an indication how long it took to import this model and to rework with your tool?
I don't know, but I'd say it's less than 5 minutes, because once it's the longest part would be to analyze your model and find the right scenario. But the beauty of it is that it's meant for an alias model, but basically it means that all your alias models, if they are all designed the same way, they will work with the same Python script.
All right, thanks.
You're welcome. Any other question? Don't be shy.
Then I have a second one. If there
Go ahead.
This tool, in your opinion, how it would help with civil engineering models, like road designs, civil 3D models or MX models? Is it suitable for that kind of data, or not that much?
Basically, if you have a CAD format, a CAD file, it means you should use Pixies, basically. The thing is, we have different solutions, so depending on the complexity, on what you want to achieve, is it something repeatable, is it something meant to be imported only once, you'll have to go to different solutions. So Studio would be the big tool, and it can be used in batch also, but the plugin is also very powerful, the plugin for Unity, and there you will maybe do things once, twice with some small model, CAD formats, anything. We also import, of course, mesh models like FBX, GRTF, OBJ, that can also be optimized with our algorithm for meshes. But yeah, I think that covers your question.
Okay, thanks.
Yeah, if you import a model inside the Unity, and then in the CAD side you do an update, how do you handle doing the update? Do you simply re-update a new model, or do you allow some kind of updating to do?
That's why we implemented in our plugin what we call the rule engine. The idea would be for you to create your intelligence only once and repeat that if the model is re-imported and updated. So I sometimes give an example. If you have a Revit file, for example, that has lights like this or only cylinders, and you have nice probe in Unity that you bought on Unity Store, and you want to, you can automatically replace all the cylinder comings from the Revit at import and replace that by a probe, a beautiful one. And since if you update your Revit files with more cylinders, more lights, well, basically, you will use the same rule. So you've created your intelligence once, you just need to re-execute that.
Okay, thank you.
Hi. Can we use the Unity plugin on its own, or do we still have to get the Studio application?
It's two different products. So you have Studio, which is a standalone product, and you have the plugin, which is...
But the algorithms and the processes are in the plugins as well.
Yeah, that's the third thing I want to talk about, is that in the plugin now you also have what we call a toolbox. And basically, when you're in Unity in editor mode, you will be able to access some of the powerful algorithms that we have in Studio. Not all of them, of course, but very important ones like merge parts, create UVs, do decimation, hidden removal, that kind of stuff.
And,
yeah.
Okay. And do we have to have the step file, if it's a step file, inside the Unity editor, and then at runtime it's not there anymore, or can we do that at runtime?
You can use the plugin in different ways. Either you're editing your editor mode that you're importing, and you create a prefab out of it, yet there's no link to your step file. Yeah. And you can also build some application with Unity and incorporate our plugin for runtime use. So that, for example, you create an experience for your customer that would be a CAD viewer. You can put our plugin inside, remanage it, and you can then deliver an experience that can load CAD files at runtime.
Excellent. Thank you.
You're welcome.
Hi. Hello.
Hello.
I've noticed that a lot of the tools within Pixies are focused on graphical performance. Mm-hmm. I was wondering if you also have plans to take into account more functional metadata, like center of gravity, constraints, stuff like that.
Like kinematics or stuff like that?
Yeah, kinematics as well, yeah.
We don't do that ourselves. If you use the plugin, for example, I think the best way would be to create your own behaviors with scripting, and by using the information from the CAD, the product structure, the scene graph we deliver with the format. Thing is, most of the time, as I said, the pivot points information or kinematics information are not kept or not, available in the file, so you cannot really use that. But there are some workarounds. For example, it happens a lot that you have your skeleton information that's placed in an XML file or in an Excel file, and you can just use scripting to then map your structure of meshes and your structure with all the information regarding kinematics, and you can script in Unity to create your animations. That's what we do with the plugin when we import a VRED scene, as I didn't show you. It's basically we keep all the animations because we are just transforming this information into a file and then we recreate components and behaviors to have the animations automatically imported inside Unity. But it's the only format that does that for the moment.
Okay. Thank you.
You're welcome.
Hi, thank you for the talk. I was wondering, in the first steps of your data preparation, you said that you have to choose between the variants that you have. Like if you have 2 hoods, you have to choose for one. In our case, we have a lot of those variants and we want them to have them in Unity and switch between them. Is this any problem in the automatic pipeline there?
No, it's more complex sometimes to build. It's just that what's weird about this model here is that it's present twice. It's not like you would have in VRED, for example, one switch node with 2 positions. That's why we needed to remove them. But once again, with the importer for VRED files, we keep the variants also. We also create components and we ship that with basic viewer where we can change variants if that's something you need. But with the Python scripting in Studio, you can retrieve information from everywhere to recreate variants. And in the next version of Pixies Studio, which will be released next month, we have a variant manager. So basically, if you can recreate variants, but it's not that very often that it's shipped inside the file, so we don't really have them. But with the Python scripting, you can recreate them and maybe put that information in an XML file or Excel file and reuse that in Unity. But there are many ways actually to do that. Okay. But yeah.
Okay, thanks.
You're welcome. We have 2 minutes left.
One more quick question. For example, typically on the car, the 4 tires are the same.
Yep.
Do you have algorithm to detect that so that the mesh is the same for the 4 tires?
Yes. Most of the time with CAD files, there are instances, like I said. So basically, you would have only one sub-assembly for one wheel, and it will be repeated 4 times. So when you do the job once, it will be just automatically, done for all the others because they share the same reference.
And so the pivot would also be properly oriented.
Sorry?
The pivot of the tire would be also mirrored.
Yeah,
properly.
if you do the same, on this sub-assembly of the left wheel, for example, you do a process, it will be the same for all the others.
Okay, cool.
But you have to be careful with the matrix and stuff like that, of course, to not break, instantiation. And in the plugin, if you import, an assembly that has instances, it's being kept. So we create several game objects that just share the same mesh render. So it's kept.
And for your LOD, can we have different LODs based on different parts? For example, the body, we don't want LOD1, but for the tires, we would want.
In terms of
already scripting, right?
Sorry?
It would be already scripting to choose which part would benefit the LOD.
In Studio, it's where you prepare the LODs, but we don't have anything in our viewer to just choose which one you want to display. But you can still export that, smartly to have LOD0, LOD1, and LOD2 in your structure. But in the plugin, it's a little bit more powerful since you can create LODs on the fly at import. So basically, you want to say you have the same, component than from Unity in the import window, and you can say, okay, LOD0, I mean to have it a fine tessellation. A second one should be coarser, and etc. etc.
So it's almost per instance that you define the LOD details. Yeah. Cool.
Okay, we have 5 seconds, so we're done, I guess. Thank you very much, guys. Have a good day.